Okay, we have the second talk of the day, which is going to be by Giacomo Tendas, and the title of the talk is Regular Theories from an Enriched Point of View. And Giacomo, take the stage.
Thanks very much, Ivan, and thanks for the invitation. It's nice to be back for a second time at Ithaca. Okay, so what I want to talk about is a joint work with Rosicky. And the idea is that we try to do regular logic within the framework of enriched category theory. So now that you know all about enriched categories, mines are just the simple one in the single object, enriched over the single object by category. So hopefully you can follow this. Anyway, so what's happening in this talk? Um, let's start from the beginning, so from ordinary category and ordinary logic. And I will start by telling you of what's the connection between regular logic, so the kind of logic where you're allowed to use equations, relation symbols, disjunct conjunctions, sorry, and existential quantification, and other categorical machinery that, in some sense, that we see in this theorem below, are equivalent to one another. We will focus mostly on these two. Okay, so what's the various equivalences that I want to talk about? It's this one, and it's a theorem that you can find putting things together from Adamek and Rosicky's book and Johnston's Sketch of an Elephant. And it says this: the following are equivalent for a category A. A is the category of models for a regular theory T on a certain language L. So you take all models and homomorphisms between them. 2A is a finite, but ignore this, injectivity class in some presheaf category, or more generally in a locally finitely representable category, but presheafs are enough. Three, and these are the closure properties. A is closed in a presheaf category under certain limits and colimits, under products, filtered colimits, and something called pure subobjects. And 4, you can actually write A as a category of functors that preserve a certain limit and colimits, namely finite limits and regular epis out of a regular category. And all this provides different point of view for the same theory. And what I want to focus on today is the first two, even though, depending on what you are working on, you might prefer 3 or 4 instead of these two. Okay, so maybe before I move on to enrichment, let me tell you something more about these two. So maybe you don't really have an idea of what's a regular theory, you don't really have an idea of what's an injectivity class. So let's recall something about that. Just a very short 3-minute course on model theory. A language, let's just fix notation, or also called a signature. You can think of it just as a set of two kind of things called operation symbols, usually denoted with F or tau, depending on your alphabet, and relation symbols. And each of these comes with an arity, which is a natural number that tells you how to interpret it. Out of this, you can build terms, and after you have terms, you can build formulas. And formulas can be of this kind. You can have equations between terms. You can have relations applied to a term, and then you recursively construct conjunctions and existential quantification. Okay, then once you have this, and you have a structure, so something that for each operation symbol comes equipped with a map, an interpretation like this. So it's a set together with a map like this. And for every relation, you have a sub-object in your M to the N. So that's given a structure, you can in logic, you can always define for any formula phi, the subset of M to the N, depending on the arity of the formula, of all the elements that satisfy that formula. And you do this recursively on the construction of the formula. And the case of interest for us is existential formulas, because I want to talk about regular theories. And so if you're given psi, how do you construct in a formal way, if you want? The subset phi m, where phi is the formula exists y psi xy. Well, okay, so if you are given psi, let's say it's in two variables, that's interpreted as a subset of m times m. So you can project down into m, so you have an element here, which as a subset is mapped to itself, and now you go to just x. What you take to define the interpretation of this guy is just the epimonal factorization of this. Because then this is the subset of M spanned by all points for which that are in the image of this. So for which there exists a Y satisfying phi x, psi xy. And let's keep this factorization in mind for when we want to try to generalize this to the enriched set. Okay, very trivial examples of von Neumann regular rings, where you have the axiom of rings, which are just equations, so I didn't write it down. The regular part is cis, saying that you have a certain pseudo inverse. So for each A, there is X, A equal AXA, or even divisible groups, where again, you have a certain batch of equations saying that something is a group, plus the existential quantification saying that it's divisible. So for any G, there is an fixed N. For any G, I can divide G by N. So there exists H and H equal G. Okay, so that's a quick recap on regular logic. Let's see something that maybe people know less, which is injectivity classes. And stop me at any point if you have questions, of course. Okay, so injectivity is something that can be defined in any category. So from this point of view, it's very general. So assume you are given a category K and an object and a morphism H from X to Y in K. We say that another object, A, is injective with respect to H, or H injective, if you have this property. So for any map into A, there is a factorization through H. Okay? Sorry, without the unicity. I wrote it, but I didn't say. So there might be more than one. Equivalently, if you want, again, to write it in a formal way without involving sets, which is useful when we want to generalize to the enriched context, this is saying that the post-composition map is an Epping set. Okay? So you can write every map from X to A as the composite of H with something else. And now an injectivity class is just the collection of all objects that are injective with respect to a certain class of morphisms. And now we'll see a few examples to make things more concrete. So going back to the divisible groups, they can also be seen as an injectivity class very easily, because if you take a group, let's go back to blue, say an abelian group, and you consider the maps Hn, so for a fixed n, which takes multiplication by n, then to say that a group is divisible is just to say that it is injective with respect to this, because to give a map from Z to A is exactly as to give an element in A. And to give a factorization, maybe I changed which letters did I use just to make it right. That's good. Uh, to give a factorization here is to give an x in A such that uh, wait, okay, mix the notation with regular rings, but who cares? Such that nx is equal to A. So Hn and inch is exactly the category of divisible groups, abelian groups. But then you have even more interesting examples where whatever you find interesting. If you go to the category of simplicial sets and you take as H the inner horn inclusions, then injectivity uh, defines quasi-categories. So where the idea is always that quasi-categories are as defined as those where you can fill uh, triangles. Um, and so on. If you are in the category of metric spaces or topological spaces and you take as H the inclusion of the discrete space with 2 points into the interval 0, 1, picking up the endpoints, then injectivity tells you that for any 2 points, x and y in your space, you can find a path between them. So injectivity with respect to this H is are path connected spaces. So in some sense, you can really express a lot of stuff with injectivity. And both, and as I said before, both approaches uh, are equivalent in this sense of this theorem, but you might prefer to go from one to another depending on the context. Injectivity becomes less tractable when, well, you have too many conditions to satisfy all at once. In that case, it might be easier to write down a formula for it and see that your model satisfied. Okay, so what do we do now? We move to the enriched context, and I try to tell you what we know and what we wanted to do and what was our motivation. Okay, so enrichment over a monoidal category or one object by category. We replace set with a symmetric monoidal close up, whatever you want. Uh, Category V. So enclosure is important for us because as we'll see below, we will really need this property of objects being exponential in some sense. So we want a bijection between maps from A tensor Y into B and maps from A into BY for a certain object BY, which is usually also denoted like this. Examples to keep in mind: set if you don't care about enrichment, but also abelian groups, graded abelian groups, cat if you care about two categories, or simplicial category with simplicial sets, and so on. Okay, so once we have fixed this, well, yes, here there was a reminder about what a V category is, but you have Om objects instead of Om sets everywhere. So I'm sure many people will have seen some instance of V category. Okay, so what do we want to do? What should be true in this context? So look at the should here. I'm not saying this is a theorem. We would like to have an analog of the theorem from before. So we would like to have what? Some notion of regular enriched regular theory for which we can consider models, and which would provide an equivalent approach to enriched injectivity classes, which have been considered before. So these things exist, as well as compare them with closures under certain operation, which have also been considered. And well, in future work, we will also like to compare them to notions of regular rich category. So there have been many notions of regularity in the enriched context. Well, it's still not clear which will be the right one to fit in this theorem. So for today, let's leave this out and let's try to connect only these. And okay, so as I said, injectivity classes have already been considered and have proven themselves useful in the enriched context. They were studied by Luck and Rosicky in the paper Enriched Weakness. And the idea is very simple. Uh, well, what you do is you fix a set of maps or a class of maps E in your base of enrichment. Think of them as surjections, or APIs, but they may not be. And then you define injectivity exactly as previously, with respect to the formal way of saying it, by saying that an object is injective with respect to an arrow if oming out of that arrow gives you a map in E. And that's what Luck and Rosicky studied, and they also proved something connecting 2 and 3, as well as me and Rosicky also proved something connecting 2 and 3. What are some examples of classes of interest? Well, a natural choice, if your category is good enough, so if it is a variety, planetary varieties, is the class of regular APIs. But in other cases, so like cat, you have either the surjective on objects or the retroct equivalences also provide very interesting applications. But then if you start adding examples, you can also be more adventurous. And like if you consider metric space, you can consider also dense maps and get even different notions of injectivity and so on. And then if you consider posets with joins of countable chains, you also have a notion of dense maps there. Since it will also appear later, I guess everyone knows what a dense map is. It's just something whose, when you take the closure of the image, you take the whole thing. Okay, so that's the setting in which Luck and Rosicky work and prove their theorems. In our setting, well, we'll see it later, but we will need to assume E to be part of a factorization system. And then I will give you some examples. Okay, so how do we do this enriched regular logic? Well, I will not say exactly what we do because that will take too much time. I will give you a flavor of what happens. So first of all, we have to deal with terms and formulas. And okay, ordinarily, as I mentioned, when you have a term, you have an arity, which is a natural number. And when you interpret it into set, then its interpretation is a function from n to the n is the arity, into n. And similarly for formulas, they are interpreted as subset of m to the n. In the enriched setting, instead, when you have an operation symbol, its arity will be a pair of objects of V without the arrow middle. So when you have an object in V, the interpretation of your operation symbol will be something of this form, from m of a morphism from m to the x into m to the y. And that's where I'm using the monoidal clause, the structure of V. And similarly, we will define formulas where you can put variable, or you can assume them to be one variables, which will have arity, again, an object, and then their interpretation will be a subobject of m to the x. So what changes with respect to ordinary logic is that you are allowed to have more freedom with these generalized arities. For instance, if you are in AB, the fact that you have an arity that is not just the free group Z, but Z to the n Z means that you can define operation whose domain is not the whole m to the n, but is the subgroup of all little m for which nm is 0. So you can define interpretation in subset. And similarly with pos, with the category of posets, if you take the arity, which is the chain with two elements, you can interpret operation where you restrict the domain to all those pairs in M, where one is less or equal to the other, and so on, similarly with matrix spaces. Okay, so that's involving terms. And from the point of view of existential quantification, well, as I said before, we fix a factorization system. And then we do the most trivial things one might do when defining what is the interpretation of a formula that involves existential quantification over something that has already been defined. We simply go and do again the EM factorization as we did as I explained in the ordinary context. So we take the interpretation that we already have, project down, and that will be the interpretation of existential quantification. Okay, so that's a quick way to say that how things change from ordinary to enriched. We have non-discrete arities, and existential quantification takes on a different meaning because we are not considering surjections anymore. Right, and let me maybe give you a few examples and then conclude. So I mentioned before the category of matrix spaces, and with the factorization system given by dense and closed embeddings, well, the important part is the left one. So the left part are given by the dense maps. And we can consider the formula, the regular formula phi xy, which is in some sense giving, again, path connected space. So for any x and y, which are of arity, this is the arity, the terminal objects, there exists P of arity, the interval, satisfying this equation. If you interpret this formula with respect to surjections, you get the usual path connected spaces, but if you interpret it with respect to this, you get something different. So what is, let's say you have a matrix space M, and that M satisfies the formula phi. If this is your metric space, this means that for any 2 points, existence is up to epsilon in some sense. So for any 2 points, you can always find a path between any 2 other points which are arbitrarily close to x and y, but not necessarily a path between x and y themselves. So the distance here is as small as you want, but it may not be 0. So these are sometimes called almost connected. And an example of this, I guess, is the usual counterexample for a connected thing that is not path connected. So I will try to draw it, but I will fail miserably. It's, sine of 1 over x, that guy. Like, yeah, terrible. So it's like x sine 1 over x for x greater than 0 together with 0 times minus 1, 1. So this satisfies this property, but it's not path connected. Forget the drawing. Other examples, well, I didn't leave much space. If you consider cut and take E to be the surjective on objects, you can express categories with limits, with chosen limits, sorry, not with chosen, with limits of some shape, say C, as the models of a regular theory. And the trick is easy, is simply that, well, something of arity C will give you a functor from C into your category, let's call it M, and something of arity C when I join some object will give you a cone over some functor into M. And so you can literally write down the formula for satisfaction of there exists a universal cone and so on. And similarly, well, not similarly, but differently, if you take a topos with the happy monofactorization system, our logic, in some sense, extends the internal logic of a topos because, I mean, you clear the regular part of the internal logic of a topos because, well, the way we construct existential quantification is exactly the same way. The difference is that since we allow um, uh, non-discrete arities, uh, we have more terms than in the actual internal logic. So in some sense, there is more that we can do. And yeah, so this was just to give you an excursus on what we are working on, and this is very much work in progress. One thing that, for example, is not clear yet is, again, in the case of cat, whether we can capture or not the case of retroactive equivalences, because they are very useful to express categories with flexible limits, for examples. But they do not form a factorization system, so we might need a way around that. But yeah, and there are many other things we want to explore. And yeah, that's it. Thank you very much for the attention. Maybe I still have more time, but who cares?
So thank you very much, Giacomo, for your talk. And now we move to question time. I see a hand by Igor, so maybe we start with Igor.
Yes, very nice talk, Giacomo. Thank you for that. How much do you need to adjust in order to capture strongly regular, enriched theories, perhaps with the aim to
Um,
show, to show that
so,
these are the ones that come from enriched operands?
so with strongly regular, you mean what do you mean?
I mean that you have same variables from both sides which do not which appear in the same order, and that's it. Yes.
I really haven't thought about it.
Yeah, okay, okay. I mean, there's a theorem which says that these are exactly those theories which can be described by operands, you know.
Uh-huh, uh-huh.
So,
Okay, I will have a look at it and
okay,
see if there is anything I can say. Thanks.
okay.
There's a nice paper also by Zavadorsky about this. So we shall move to the next question. Christoph?
Yes. So thank you for the talk. And maybe one nice property of this regular fragment in the classical setup is that it's closed. I mean, the category of models is closed under reduced products, and that can like you can use that to show that even kappa regular logic is, I don't know, complete or something like that. So there are enough set models. And maybe a test question for this enriched kappa regular logic is that when is it true that like a kappa regular VE enriched theory has enough models in V itself?
Right. Well, if E is stable under products, then your models will be closed under products and filtered colimits, so they will have reduced products. But beside that, I don't know. Well, I haven't tried to go farther than that. Yes. So yeah, thanks.
Thank you.
Do we have other questions? Okay, we are also on the border with time, so we thank the speaker one last time. Thank you, Giacomo, for your talk.